Okay, so we worked with this theorem, and this is where we finished. We finished proving that if you have a path and you compose it with a complex function, then the result is another path, right? And if the path and the complex function are differentiable at the corresponding points, then the composition will also be differentiable. And here we have our formula for finding the derivative of the composition. Okay. Now let's talk about how to describe the angle between two curves. So here's what we want to do with this. What do we want to do? Okay, sorry, I'm just trying to see here. Like, here's the idea of what we want to be able to do. We want to be able to describe, say, now this is C, okay? So this is a complex plane. Maybe from here, say from here to here is gamma 1, and like, say from here to here is gamma 2. Okay, now we want to describe that angle. Right, so how do we describe the angle between two curves? So notice that in this situation, we will have some point, we could call that point Z0, where the curves intersect. So that means there exists some point T1 and some point T2 in R such that Z0 is gamma 1 at T1 and it's also gamma 2 at T2, right? So here's how we're going to define the angle. Basically, we're going to look for the tangent. We're going to use the tangent line to the curve at that point, right, to the curve of y1, and the tangent line to the curve of y2, and then we'll measure the angle between those tangent lines. Now, how are we going to figure that out? Well, anytime you're talking about tangent line, we know that the slope of that tangent line is given by the derivative, okay? So that's why we're involving derivatives. Now let's look here in this definition. The angle between gamma 1 and gamma 2 at Z0 is the angle whose argument is the argument of gamma 2 prime at T2, right? So we want to say the angle of, take the angle here minus the angle of gamma 1 prime. Now, do you remember when we were talking about multiplying numbers, and we said that the argument of Z1 times Z2 is the argument of Z1 plus the argument of Z2. Do you remember that? So this was when we were first working with polar coordinates. And so we said that when you're multiplying complex numbers, you are adding the angles, right? So this theta is seen to be the amount that you need to add to this angle here to result in this angle here, right? So you're asking, like, how much do you need to add in terms of angles to get from the derivative of gamma 2 at T0 or T2 to the derivative of gamma 1 at T1. So let's look at this. So what we're saying is that theta plus the argument of gamma 2 prime at T2 is equal to the argument of gamma 1 prime at T1, right? Because this now is going to be, this is the same as the argument of multiplying those two together. So solving for theta, we'll just get, or wait, I think I did it the other way around. So it should be, that theta is equal to this plus this. So adding theta to the argument of gamma 1 results in the argument of the gamma 2 prime at T2. Okay, so this is our definition. Now, embedded in the definition is a couple of assumptions, a couple of requirements. So provided that there exists gamma T1 and T2 such that, so this is saying that we need the curves to intersect, because imagine if you had two curves that don't intersect, how do you discuss, right? So say if curves here, how do you discuss the angle between them? Doesn't make any sense, right? So we need for the curves to intersect at some point z naught. And another thing that we're going to require is we're going to require our curves to be regular at that point. So that means gamma 1 prime of T1 can't be equal to 0, and gamma 2 prime of T2 can't be equal to 0. Okay? So again, there's some ambiguity of defining the argument of 0, right? 0 being the origin. There's some ambiguity because if you set r equal to 0, then for any theta, you're still at the origin. Okay. Now here's the key result. Now this is what we're studying this for. Conformality. This basically says that angles are preserved by holomorphic functions, assuming that that derivative is non-zero. So let's look at it. So we're saying if you've got some regular curves at a point and the curves are intersecting, so you've got, so say here's gamma 1 and here's gamma 2, and they're meeting at z naught. And if f is differentiable at z naught, now when we apply f composed with gamma 1 is going to be a brand new curve, right? So maybe this is f composed with gamma 1, and then I don't know, maybe f composed with gamma 2 looks like that. And what we're saying is that if f is differentiable at z naught and the derivative at z naught is not equal to 0, then this angle here is the same as this angle here. Right, but imagine again we're doing the tangent. Let's see if I can do this better. So if I were truly try to do the tangent lines, so then I would be talking about here and here. So my theta would be like that, right? So what we're saying is that holomorphic functions whose derivatives aren't equal to 0 will preserve the angle between curves. Okay? Now, one thing to note in terms of understanding this, holomorphic functions do not preserve length.
It's 1945.
So every time we're in C, so think of it, see if you have a point in C, then you can describe Z in terms of an angle and a distance, a length. The length meaning the distance from the origin. Right? So Z depends on the R and the theta. Right? So what we're saying is that if F is holomorphic, then F is going to preserve the angles, the theta part. F does not preserve length. There's no, so let me write it here. It does not imply F preserves length. So let's look at a couple of examples. Key example. Let's look at, so our first example, let's say is f of z equals z. This is definitely holomorphic, and this definitely preserves length, right? Because it's identity. So this preserves length, yes. But what about f of z equals z squared. Does that preserve length? No, it does not. Remember, if you have a point that is inside the unit circle, right, and we're applying f, which is squaring, that point is going to be sent closer, right? So that angle is going to be doubled, right? So the angle is going to be doubled, like to here, and it's going to be sent closer in. Does that make sense? So length is not preserved, right? Because look, you're going to lose length. If you've got a point that's outside, when you square that point, it's going to get moved even further out. So it's like you're doubling that. I don't know where it'll end up. But the bottom line is that length is not preserved by this function, which is definitely holomorphic everywhere. Now here's a question. Let's look at this f of z equals z squared. Does this preserve angles, right? Is this conformal? So the question is f of z equals z squared conformal? Because it's holomorphic, right? So according to our key conformality result, right, angles are preserved by holomorphic functions. Well, let's look here. Imagine if I have imagine if I just I'm just going to do this at random here. So say if I've got I don't know, let's see. Maybe this is my first curve and this is my second curve. So this is gamma 1 and this is gamma 2, right? Now, when I apply f, what's going to happen to theta? Because remember, theta is this angle in between them, right? Well, now, if we take 2 points here, remember, and imagine we take 2 points here that are on the unit circle. We're rotating, so we're going to end up with theta being doubled. Does that make sense? So the angle after applying theta is going to end up being twice as big. Yes? So this gamma 1, wherever that is, like say this is 1, or say that say this angle right here is pi over 4. That, when we double it, is going to move this point to I, right? And this point here, which is I, if we square it, this angle, which is pi over 2, is going to be double. So we're going to end up at negative 1, right? So the angle between them, the new angle, is now twice the old angle. Right, so if this is my old angle, my new angle is twice as big. My old angle was pi over 4. I think that's angel. Angle. How do we spell it? Angle. Yes, that's better. My new angle would be pi over 2. What happened? I thought that holomorphic functions were supposed to be conformal. We did not preserve angle. We doubled the angle. Here's what happened. Remember, we've got this requirement that f prime at the intersection is non-zero, right? So here, our intersection point is the origin, and f prime at the origin, right? What's f prime of 0? It's going to be 0. So f of z equals z squared is not going to be conformal when you're talking about curves that are intersecting at the origin, right? Because we're not going to satisfy this requirement here. Okay, and I have another example just to show that length is not preserved. The purpose of this function is to stretch the length, right? So whatever you had before is going to have a length or an R value of 100 times the original one. Make sense? So this is a very easy way to see that lengths are not preserved by holomorphic functions. In some cases, under some scenarios, angles are preserved, right? So what we need, again, is we need the gammas to be regular, which means their derivative is not going to be 0 and at the point. And we also need for f prime to not be equal to 0, okay? Then we can be assured that our holomorphic function is going to be preserving angles. Okay, so let's move on to the proof. How we want to show this. Here's what we want to do. We want to show that if f is holomorphic, then f is conformal. And again, under the assumption that our f prime of z naught is not equal to 0, our gamma prime of gamma 1 prime of t1 is not equal to 0, and gamma 2 prime of t2 is not equal to 0. Right? So all of these 1, 2, 3, 4, these 4 hypotheses are supposed to result in it being conformal. What does this mean? This means that if we've got our gamma 1 and gamma 2, we want to show that this, which is the angle between f composed with gamma 1 and f composed with gamma 2, is the same as the angle between gamma 1 and gamma 2 at that point, right? And so this gamma 1 here is going to be the argument. This is going to be the angle that you get going through the argument of gamma 1. So I think this actually might be a typo here. Excuse me. Yeah, this right here should be gamma 1 prime at T1, and this should be gamma 2 prime at T2, right? So we're saying that is the, right? So we're saying this angle between the two curves is the same as the angle between the angle between the two curves when you compose them with the holomorphic function. Okay, so let's get to our proof. This is what we want to show. So we're going to do a sketch here. And here we go. Now, this is going to fall from the chain rule. Remember we proved the chain rule? So we want to show that the argument of f composed with gamma prime at T1 minus the argument of f composed with gamma, that should be gamma 1, gamma 2 prime at T2, that this is congruent mod 2 pi to the argument of gamma 1 prime T1 minus the argument of gamma 2 prime T2. That's what we want to show, right? So let's just work with the left-hand side and see what we get. Now we've got our formula, so we'll say recall that f composed with gamma 1 prime of T1 is going to equal f prime of gamma 1 at T1 times gamma 1 prime at T1. Why? We proved this. This was the last theorem that we proved, and we looked at remainders and all of that. Now, gamma 1 T1, that's the same as our Z naught. So we've got f prime of Z naught, and then gamma 1 prime T1. Okay? And similarly, the derivative of f composed with gamma 2 at T2 is going to be f prime of Z naught times gamma 2 prime T2. Okay, so let's just plug this in. So the argument of f composed with gamma 2 prime of T2 at T2, sorry, minus the argument of f composed with gamma. I've got this all mixed up. I should have, well, if we're doing 1 minus 2, 1 minus 2, okay, that's fine. Let me just switch these to 1. Gamma 1 T1, gamma 2 prime T2 is going to equal the argument of F prime. So what I'm doing is I'm replacing this with this. So F prime of Z naught times gamma 1 prime of T1, right? And then minus the argument F prime of gamma 2 of T2, but that's the same thing, it's just cancel. That's gamma, Z naught. And then we've got gamma 2 prime of T2, okay? Now, this is a complex number, and this is a complex number. So the argument of the product is the sum of the arguments. So this is going to be the argument of F prime of Z naught plus the argument of gamma 1 prime of T naught minus, we'll do the same thing here, right? The argument of the product is equal to the sum of the arguments. So we'll have the argument of F prime of Z naught plus the argument of gamma 2 prime of T naught. And now we're happy because this term and this term are going to cancel each other out. So we're just left with argument of gamma 1 prime T1 minus the argument of gamma 2 prime T2, right? And isn't this equal to the angle between gamma 1 and gamma 2? Yes? So we started off with this, which is the angle between F composed with gamma 1 and F composed with gamma 2 is equal to all this is equal to, and we end up with it's equal to the angle between gamma 1 and gamma 2. So now one of the questions you might be asking is, Kalila, where did we use the requirement or the hypothesis that this F prime of Z naught is not equal to 0? And here's where we used it. We used it when we went from here to here. So when we say that the argument of the product is the sum of the arguments, we're able to do that and have that be well defined because our derivatives aren't 0. Okay? All right. A few last words. Beware. It is not the case that conformal always implies holomorphic. So for instance, we've got a function here, f of z equals z bar. It's conformal up to a sign, right? You're only off by a plus or minus, but it doesn't preserve angles. And we know that this is, does not preserve angles, but is not holomorphic. It's not holomorphic. Sorry, that's a typo there. But I will refer you to, and you should read up in section 2, chapter 2, section 13 in Saracen for details. There's a little section that Saracen goes through and gives some conditions under which conformality does imply that a function is holomorphic.